n naught minus 3, and that's a series, n naught times n naught minus 1 times n naught minus 2 times n naught minus 3. And if you remember what a series is, you can recognize that as n naught factorial, right? 10 factorial is 10 times 9 times 8 times 7 times 6. And if n naught is 10, that's this situation right here. So that's why you take calculus. That's why you take mathematics before you get into the good stuff. So I don't have to teach you what factorial is. You'll have already seen it. So now your math is paying off. You're welcome. All right. So, is the liquid any different if we switch these two? No, not really. What is different? So we switch this and we switch this. What's changed? The nearest neighbors are different, right? This guy has 3 red nearest neighbors and 1 blue nearest neighbor if we take the corners, or it's just got 1, 2, 3. This has 3 red nearest neighbors, but it's also got 2 next nearest, or however we want to do it. So the microenvironments are different. But remember, we're making a mean field approximation, right? So all of the blue lattice sites experience the same forces on them. The microenvironment doesn't matter. Okay, more math. Here is all the number of ways that we can put these A and B sites on there. You'll just have to trust me that this is true. Here is the entropy, so remember this is the distribution, or all the number of ways we can put the sites on, which is given by this equation right here. Here's Boltzmann's constant. You can look up Boltzmann's constant. What does Boltzmann's constant refer to? What is Boltzmann constant really all about? What type of quantity is it? You remember what the ideal gas constant is, right? What's the symbol for ideal gas constant? R. And R, what are the units of R? Joules per mole K, right? So R refers to moles. Boltzmann's constant refers to particles or molecules. So K is just the molecular version of R. So R and K are exactly the same thing. And if you want an equation, K times Avogadro's number equals R. Or the Boltzmann's constant times 6 times 10 to the 23rd particles per mole gives you a molar quantity. And we know that the ideal gas constant and the Boltzmann's constant are all about energy. So the ideal gas constant doesn't have anything to do with gas, although we use it that way. Ideal gas constant really has to do with energy. Okay, little lesson in Boltzmann's constant for you. We compute the entropy, and the entropy is going to be negative in this case because we know our Spidey sense tells us that when we mix two things, the entropy is going to be negative, right? It's going to increase. And so, scratch that. But this is the form of the equation right here, and then the mole fraction is just the moles of A over the total moles, and the mole fraction of B is the total number of moles, or the number of moles of B over the total moles. So X is the mole fraction, and N is the number of moles. So you can review this and check this out as we go forward. Okay. And here's entropy of mixing per molecule, which now we have Boltzmann's constant right here, and per mole we have R right here. And so the only difference in these two equations, if you look very carefully, is K versus R. So make sure you familiarize yourself with when you use Boltzmann's constant and when you use R, the ideal gas constant, because they mean the same thing but on a different quantity basis. Okay, we have 2 more minutes, so I'm going to tell you about polymer mixing now. So whether we have polymer solution, right, or a polymer blend, this is the lattice model. So now, what's different between this picture and the lattice model for mixing 2 small molecules? That's right, we have a centipede now, and that centipede thing is called a polymer, and we know that polymers are connected to one another. And so this adds a mathematical constraint onto our lattice model, right? Now we just can't put the blue beads wherever we want. They have to be next to another blue bead. And so we need to have these all connected, and then we fill in all the rest. So remember, a nice polymer solution is polystyrene and toluene, so you can connect the molecules to what we're doing. You know that this is a lattice model, and so now we have a completely different, or we have a different situation that requires different math to analyze. Did I see a hand go up? No? Any questions? All right, last slide. Second to last slide. The entropy of mixing polymer in a solvent, we can just write it down. So let's just write down this result right here. And we call this Flory's result. Do you know who Paul Flory is? He's the father of polymer physics in the United States. He won a Nobel Prize for studying polymers. And so because he won a Nobel Prize for studying this, I don't need to derive it. You can just take it as true. And so you can think about now how small molecule mixing is related to polymer mixing. And also you can think about volume fraction. So you notice that we have phi's here instead of mole fraction. And that's because how many polymer molecules are in this lattice? 1. So the mole fraction is a lot different, right? So we need to take the volume or the area in a 2D model, but let's say volume. The volume difference, so that's what the phi's are right here. Paul Flory, I told you, is the father of polymer science. He's interesting because he worked at DuPont with Wallace Carothers, who's another very famous person. He was a professor at Cornell. He was also a professor at Stanford, and he visited Penn State back in the day. And so Paul Flory, he's passed now, but a lot of polymer professors in the US know who Paul Flory was, and were learning polymers at the same time that Flory was writing his book and winning Nobel Prizes. And those people still exist today. So you can meet Bob Grubbs, you can meet Alan Heeger, you can meet some of the other Nobel Prize winners in polymers if you go to the right meetings. So thank you very much, and Professor Zarzar, we'll see you on Friday. Thanks.